K.V. Rao. I'm working as assistant professor in National Engineering College. Today our topic is PN junction diode. Okay. In this PN junction diode, what we are going to see is how can we form PN junction diode, right? Next, biasing of PN junction diode and its characteristics. This is what we are going to see, right? Okay. What is PN junction diode? Now how can we form PN junction? So one type of P types, either P type or N type, is connected to other type. That is, P type and N type semiconductors are combined together and it leads a PN junction diode. In this process, in the junction, it means one side we are having P type, another side we are having N type semiconductor. In the middle we are having junction, that is P and N junctions. So in that, the junction is known as PN junction or depletion layer. It is a width of micrometers. It is a width of micrometer. It is small and thin. Right? Now how can we form these PN junctions? So for this, by following three basic methods, we can form the PN junction. And what are they? They are ground junction method, alloy junction method, diffuse junction method. Right? In these three processes, first mainly we are giving some thermal energy. That is the main concept and the common point. For the ground junction method, we are taking any one kind of semiconductor, that may be P type or N type semiconductor. We are heating that semiconductor up to some temperature. That semiconductor device is nothing but a solid state material. That's why when we heat that solid material, what happens? First it melts. Like for example, if you take P type semiconductor, we are melting that substance. For that molten portion, we are adding fifth group elements as impurities. Right? Already in P type semiconductor, we are having third group elements as impurities. When we deposit other kind fifth group elements on this molten portion, and by cooling this molten portion, we can get PN junction layer. That is what we are going to see in this ground junction method. When an extrinsic semiconductor is grown for melt, what is this extrinsic semiconductor? P type, N type. During the middle of the growth process, impurity of other kind are added to mold. That's what we discuss. Next, alloy method. In this alloy means mixture of compounds. Right? Alloy. In this alloy method, we are taking one type semiconductor and we are keeping that semiconductor upon the another type semiconductor. But let us take N type semiconductor and keep this N type semiconductor on the P type semiconductor. Now give some thermal. That's why it means heat that P type semiconductor. Right? But what happens when we heat that substance? Some impurities are fused together and it can form PN junction. Right, at the surface of P type semiconductor, some impurities of N type semiconductor fused into this P type semiconductor and it leads to formation of PN junction. Next, diffusion junction method. In this diffusion junction method, there are two types: gas diffusion and solid diffusion method. Right? In the gas diffusion method, we are taking N type semiconductor. Right? When we heat this in gaseous atmosphere, we are taking some boron gas chamber. That boron gas chamber, we are keeping this N type semiconductor. Right? When we heat this, then automatically what happens? Some gas molecules diffuse into this molten portion. Then it leads or it forms the PN junction. In solid diffusion method, we are taking P type semiconductor, N type semiconductor, and we are painting So other kind of the elements on this, and by heating that can be diffused into this first kind of a semiconductor and forms the PN junction. Wait a minute. Right? These are the methods which we are going to follow the PN junction. Then what happens? We form PN junction, then what happens? In this depletion layer, there are electrons as well as holes. It means in case of p-type semiconductor, holes are majority charge carriers, whereas in n-type semiconductor, electrons are majority charge carriers. Within this layer, combination of holes and electrons will be present. Now, see here. So in the figure 8a, left side, we are having PN, P combined with N, right side in the B, formation of PN junction with some potential barrier. It means whenever we are having positive charge and negative charge in a particular region, then some potential will be established. So we can say this is barrier width or simply potential barrier. Next, after formation of this PN junction, what happens? That due to the thermal energy, these carriers may diffuse through the junction. Right? So, combination of this hole and electrons leads to some potential difference. We are not connecting it to battery. If you are not connected to any battery, then that is so called unbiased. That is so called unbiased. Then what happens? If you are not connect any battery, then we could not expect any flow of current through them. Right? The number of free carriers are continuously reduced due to recombination, becomes diode of charge carriers. That's why in this particular unbiased system, no current flowing in the circuit. Right? And here the potential barrier, what we mentioned, potential barrier is about 0.3 volt for germanium, whereas it is about 0.7 volt for silicon. It means whenever you apply some potential difference across PN junction diode, for this much amount of the potential difference, then only you can expect the flow of current in the substance. That is, when applied voltage is more than barrier voltage, then only current flowing in the particular diode. Right? Okay. Now forward bias. What is forward bias? So forward biasing means, so see here, figure 10, forward bias circuit. So it means we are having left side p-type, right side n-type semiconductor, in the middle PN junction. So we are having battery in that circuit and also ammeter, milliammeter. So p-type semiconductor connected to positive terminal of battery, n-type semiconductor is connected to negative terminal of battery. Then we can say it is under forward biasing. Forward biasing means positive terminal of the battery connected to positive type semiconductor, p-type semiconductor, negative terminal of battery connected to n-type, that is then negative type semiconductor. Then we can say it is under forward biasing. In this forward biasing, see here first point what we mentioned. So when we apply some potential, when we apply some voltage, right? So here we have connected to battery, we are applying some voltage. Actually we are having positive terminal connected to p-type, right? When we apply some voltage, then bonds breaks and electrons moves towards the p-type semiconductor and holes moves towards the n-type semiconductor. Now combination of hole and electron pairs takes place. Combination of hole and electron pairs takes place. That's why here barrier width decreases. Barrier width decreases. Barrier width decreases. Then when barrier width decreases, then for small amount of voltage also current passes in the circuit. Right? It means when barrier width is small, a small forward voltage is sufficient to complete eliminate the barrier. It means then automatically electrons can become as free electrons. Flow of electrons is said to be current. That's why here the current flowing in the substance for small amount of the voltage. This is forward biasing. Reverse bias. Reverse bias junction means so reverse bias. See here figure 11. So PN junction we are having P-type N-type semiconductor. P-type semiconductor connected to negative terminal battery, N-type semiconductor connected to positive terminal battery. Then we can say it is under reverse biasing. See here when we connect P-type semiconductor to negative terminal battery, N-type semiconductor to positive terminal battery, these electrons drift towards the positive terminal battery, holes moves towards the negative terminal battery. Then deflection layer width increases. If deflection layer width increases, then we require more potential difference to generate the current in the circuit. That's why here in this reverse biasing process, see here in this case the applied voltage established an electric field in the same direction due to the potential barrier. So when it has been observed that the increased barrier potential prevents the flow of charge carriers. That's why we have to apply more voltage. So VI axis, that's what we mentioned. Here we have seen zero bias, unbiased. Right? When the junction is not connected to any voltage source, it is said to be unbiased. Then there is no flow of current in this process. In forward bias, so already we have seen. So when barrier height is small, 0.2 volts, after this, when the applied voltage exceeds 0.2 volts, then the junction resistance becomes 0 and low resistance path created. Then for small amount of voltage also, right, current passes in the circuit. This is called forward current. When applied barrier what is small, then the current should be in terms of milliamperes. In case of reverse bias, the barrier width is high. That's why we need to apply more voltage. That may be even 20 volts sometimes. That's why for this also the current flowing in the substance is very small. It is order of microamperes. If you see the figure 12, it shows the VA characteristics of PN junction. We are taking voltage on x-axis, both positive and negative x-axis. We are taking current on y-axis. Forward biasing for 2 volts, having more about 8 milliamperes. For 3 volt it may be around 30 milliamperes in this breakdown. So in the reverse biasing process, for large amount of the voltage we could not observe any current flow. Then sudden increment in the current takes place. That is called breakdown current. Okay, thank you.